Week 2, Lecture 1. Do you have any questions before we do our new stuff today? Okay. So, we are going to be doing one problem today, and that is from Chapter 4. And towards the end, if there's any time left, I will do some additional stuff, which is going to help you for Friday, because on Thursday, we're going to start beam elements. That means lecture on Thursday is going to be on beams, and the first hour of the lab is going to be on beams, because the homework that you're going to get is going to be related to beam problems. Okay, so the more we spend time on it, in case we have anything today, the better it is. So here's the situation. We have a disk, constant thickness right up there, and this disk is rotating at a constant speed about its axis of rotation, that vertical axis. Now, first of all, if I ask you where is the most critical area as far as integrity of this disk is concerned, I hope that you will tell me on the inside, that inside hole, okay? In fact, it's the kind of problem that you can analytically solve. And it is solved for you from a stress analysis textbook. We'll come to that in a minute. And first of all, nothing can spin by itself. Okay, nothing can spin by itself. And obviously there's a shaft there, perhaps. The shaft is turning with some other mechanism, maybe a belt or something. And it makes this thing spin. It's not a UFO, it's just, spinning with something else. But we're not going to model that. It's possible to do it, but we're not going to do it. The three components of stress that are principal stresses here are stressing the thickness direction, The thickness direction being along the thickness of the disk. And that is very small, 0 for all practical purposes, because nothing stops that from expanding or or shrinking, etc. There is no stress in the axial direction. And that's why you see a 0 as sigma axial, right there. When you look at the hoop stress is like, my belt, hoop, okay? The stress in that direction, that is the biggest stress. You can see that dark solid curve is the variation of hoop stress from the inside surface, all the way to the end. It is never 0. You can see that. That hoop stress is never 0. On the hole it is value, biggest one. On the outside, also it has a value, but of course it's not as big. You can see that. The radial stress, another principal stress, is 0 on the inside, because nothing is pushing on it. 0 on the outside, nothing stopping it or pushing on it. But if, for example, this was pressurized, hypothetically, on the outside there was pressure, or on the inside somehow you could have exerted pressure, then radial stress will not be 0. But in this case, it's just there is no pressure, it's just 0 inside, 0 outside. Biggest in the middle, you can see that radial stress is biggest in the middle. That usually doesn't happen, something being biggest in the middle. Usually the biggest stresses are on the boundary, on the outside. But this is one of those cases, the biggest radial stress is actually inside of the part, etc. There we are. By the way, this stuff I told you is coming from a course called stress analysis. There used to be, up until maybe 8-9 years ago, there were actually 2 deformable bodies course and a stress analysis course. So we got rid of the stress analysis. We call the second deformable bodies stress analysis. That's why this stuff was being covered in stress analysis course Not anymore, because you're taking really deaf bots too. Anyway, forget about that. Some information is given here: inside radius 1, outside radius 6 inches, height of 1. Now, I hope you agree with me. If this is going at a constant speed, when you take a sector, any sector, 30 degree, 30 degree, 30 degree, next to each other, these are all going to look the same. Okay? I hope you see that. If not, think about it, because I keep saying these things when it comes to planes of symmetry and things like that, and you might just, hear it from one ear and let it go from the other one. It's not going to help you. Just think about it, see why is that the case. So I hope you see that. So these sectors are all behaving the same. If that is the case, why should I bother making the whole disk? I'm going to take a 30 degree sector or a 45 degree sector or a 2 degree sector, whatever, and just model that. And that's what we're going to do. That is not important. I will take it to be 30 degrees. I can also take it to be 90. But I want to show you something new. That's why I'm not taking it as 90. Okay, I'm taking it at 45, say. And you also realize that there is a plane of symmetry halfway through the disk. If this disk is constant thickness, for example, even if it's not constant thickness, it's tapered, and it's tapered symmetrically, there's a halfway point, halfway plane that is a plane of symmetry. Now, in the book, this problem is done with, 45 degree sector, whatever it is, but the entire thing is taken, not half the plane. Today, I will do both of them, okay? And it is also possible to do this entire thing without taking any plane of symmetry, and that's just like the block that we did last week requires some thinking. How do you do that? Okay, so we'll come to those in a second. Are there any questions? Okay, so let's go ahead to CATIA. On a convenient plane, for example, on this horizontal plane, I will sketch a 30 degree sector, and then palette. Okay, so on this plane, I will sketch let me there's a zillion different ways of doing these things. That's why you may or may not like the way I'm doing it. That's fine, I understand. We're going to dimension it in a minute. And then my lines. The line goes from here to here. That's one of them. And the other one is I'm going to draw it like this. And I'm going to trim it, quick trim. So a quick trim is like that eraser that you see somewhere here. Right there. Get rid of this, get rid of that, and that, and that. Okay? Now we're going to dimension it. You've got to create this somehow. Do it any way you like, any way you want. So you need something like that because you're going to pattern. So let me put some dimensions. This is 1. It says 1 inch inside radius. Okay. This is 6. By the way, I could have drawn a rectangle for you and revolved it or shafted it. That would have given me the same thing. Are we good here? Yeah. The angle. I'm going to take a 30 degree angle. Dimension between this and that, 30 degrees. Okay. You know what happened? You see that line? It used to go through the center. Not anymore because of this dimension that I put in there. That white line on the top, it was going through that center. That's how I actually did it. But when I put these dimensions, it's not. So I have to clean it up. So here's the way I'm going to do that. I'm going to say this line control the center make him coincident, using my favorite dialog box like that. Now that line is going to go through the center. That's why everything turned green. Okay. Before, just a minute ago, second ago, it was missing the origin. That's okay. Just do it any way you can. Now, if the height is, the entire height is 1 inch, I'm taking symmetry, middle plane of symmetry, not as it's done in the book. Actually, let me not do that. Let me do that later. I will take the cut later on. I will do it just like it's done in the book, without the middle plane of symmetry. Okay, we pad it 1 inch. There we are. So this is the piece that I'm going to model. Why don't we apply some material to it? I'm not sure what I said. Probably steel. I'll make it out of steel. Apply material, metal, steel on that part, and okay. Let's do it very nice and systematically. I'm going to save this thing with, I'll call it 2 planes of symmetry, okay? So file, save management, save as, desktop, new folder. So what did we call that? Okay, so that is morning. Morning. Okay, everything is going to go there. And the name, I'm going to call it 2 planes of symmetry. 2 planes. And make sure I don't mess it up. Don't write anything, the analysis on top of that. 2 planes. Okay? I hope it went into that. Okay, good. So now we're going to go to analysis and simulation. I'll have to come back here. You'll see there's some stuff missing, and I'll come back here. But for now, let's just go ahead and go there. Analysis and simulation, generative structure analysis. CATIA immediately measures this with whatever type of element that I had. We're doing static analysis. I don't know what kind of element I had, but the size of it is taken as that. It's parabolic, fine. Oh, that's fine. That's fine. Now, one thing you know for sure, that the biggest stress is on the inside of the hole. So why don't we do local mesh refinement there in anticipation of your test? Look, the hoop stress is changing very rapidly right at the inside hole. You can see that solid curve is shooting up very fast. So I need a local mesh refinement there. I might as well do that. Okay. So we can do that here. You know how it's done. On there. That size is good. Okay. We'll come to the issue of what size is good to begin with. We haven't discussed that yet. Okay, but right now we just go ahead and do it. There, you see that it's finer around the hole, as we expect, because stresses are very changing very rapidly there. Okay, good. Deactivate this. The other day in the lab, somebody said, "I don't know, how do I put a load here? How do I put a strain?" Because I don't think it was here. Anyway, deactivate. And let me change the rendering here also. Good. So, do you agree that this is a plane of symmetry? We said that these sectors are the same. That's why we took a 30-degree sector, for example. That means that when this disk is rotating, with respect to the disk, things on these 2 planes just radially move out. That's it. They don't go to the side. They don't go left. They don't go right. They just move out. That means that plane remains a plane. That's what a roller is. Okay, a plane of symmetry. So there is nothing magic about plane of symmetry. All that means is that things on that plane do not move perpendicular to it. That's all. So instead of using surface slider, if I took one of these surfaces, one of them, and said nothing moves perpendicular to it, that'll do the job. I don't need a surface slider. It's the same thing. And that's very easy to do on this one. Of course, you can go ahead and put a surface slider there. Okay, you can do that, no problem. You can do that. But in the book, on this, not on this one, but on the other one, I didn't put a surface slider. I could have, and I will now. Okay, but this is obvious because nothing moves in the what direction would that be? If you look at your coordinate system in this drawing, nothing moves in the direction y in that on that face. And if I didn't like surface slider, if I had something against it, I can select the user defined, and on that face, I say nothing moves in the direction y. Isn't that a surface slider? That's a roller. That's exactly as a roller. So I can do it like this. But on the other plane, it's at 30 degrees. So you can't say y or x or z. You have to create a local coordinate system and select that as the displacement. Here, look. On this one, which is obvious and easy, I will actually put a surface slider. Should be the other way around, but I make it harder. On this one, I put a surface slider. I'm not going to do it like that. I say surface slider on this. It's the other one that's causing a problem. It's the other one that I have to put surface slider in it, but on purpose, I'm not going to do it like that. I'll make the harder way on that other surface. So I say fine. Again, remember, you can do exactly the same thing on this face. It'll do the job. I don't want to do it like that. I want to show you something new. Say okay. On this face, instead of putting a surface slider, I want to say nothing moves perpendicular to it. But perpendicular to it is not x or y or z. So I'm going to create a local coordinate system here. This is why I have to go back now, because you can't put that coordinate system in here. I have to go back to part design. And before I do that, let me save this. Okay. So we go File, Save Management, Analysis, Save As. In that folder, morning, right? Did I call it morning? Oh, yeah, morning, analysis, 2 planes. It'll be foolish for you to do it like this on the test or homework, but learn something new. Okay. Now let's go to that part. And to go to the part, you can get to it from here, from the tree. You don't have to, minimize this thing. You just expand this. Information is up there. Double click on it to send you to the part design. And there is this guy. See that? There's no way you can miss it. Axis system. It's called axis system. Axis system. Just click on it. And by default, automatically, it puts it at the global origin, right there. The global origin. And the directions of the X, Y, and Z are lined up with the global coordinate system. Well, it's better for me if I put it somewhere else because I can see it at least. So for the origin, I'm going to select this point. You see that? It's no longer at the global origin. It's on that top corner. It can be any other corner. And I want one of these coordinate systems to line up with that line, to line up with that edge. So for example, for I don't know, for x-axis, I'm going to select this. Notice what happened. It lined up the x-axis with that edge. So perpendicular to it is simply z of this coordinate system. See, all you had to do was just put a surface slider there. Okay, I understand. So we go back to our analysis. Again, you can double click on this. It'll send you back to the analysis. There we are. And user defined restraint on that face, but not the global coordinate system, the user coordinate system. And it says, go pick it. There. You see? It was so much easier to put a surface slider there. If it was 90 degrees, you wouldn't have that problem either. But on purpose, I made it hard because you're going to see these things. Say, okay. Good. Now, the bottom, I'm not going to put anything on it. If we took half of it, I'll put the surface slider there. Okay? Good. Let me save this. Okay. Now we're going to apply the load. You go to the load. You go to the load. That speed, that rotational speed, is actually causing constant speed around the circle. Will give you a normal acceleration, radial acceleration. Centrifugal force, mr omega squared. Remember? So it has to do with your speed, okay, your angular velocity. Okay. So look for something which is there in acceleration. It says rotation force. That is where you specify the angular velocity. It's that angular velocity that causes a rotation force, which is your centrifugal force, your acceleration in the radial direction. Okay. Axis of rotation. Axis of rotation. Well, first of all, support. Support is, this is a body force, like gravity. These are body forces. It doesn't matter what you pick. The whole thing is going to be picked. The whole thing. The whole body is going to be picked. Axis of rotation. Axis of rotation. Can you help me with this? What do I put as the axis of rotation here? What should I put as the axis of rotation? Yes. Good. Unfortunately, it won't let you take the z-axis. You see that? Usually when you right-click, you're absolutely right, z-axis. But remember, the z-axis of the global system, not that guy. The global system axis, coordinate system was over here at the global origin. But unfortunately, you don't have access to it. Okay? So you're missing a line there. You can create a line if you want, or you can create the global coordinate system there. It's already there. It's just that I have to have access to it. So this is why we can't go any further with this. I go back to my part. I go back to my part, and create an axis system. Automatically is going to automatically it should put it at the global coordinate system. Did it do it? Oh, yeah. You know why it didn't? Because that current was checked. That current was checked when I created that coordinate system. I told it, hey, use the old one. Use the coordinate system. So let me do this. Let me uncheck this and put 0, 0, 0 here. Okay? 0. Come on. Actually, let me cancel that. Let me cancel that for a second. I'll go there. I'm not going to make it current. When you do not make it current, it turns it into dash thingy. And now when I do axis system, not there. Hang in there. We got a problem. Okay. We gotta fix it. Let me first. This is not the way I was intending to go. Let me choose a coordinate. Coordinate with coordinate 0, 0, 0. A point with coordinate 0, 0. 3 zeros. So where's the point? Point. Okay, right there. I was not planning to go this route. I created a point at 0, 0, 0. Right there, you can see that X, white X. And now, axis system. There, I put it there. It is this Z axis that is the axis of rotation. It's this Z, okay? So we go back to our analysis. That rotational force, we took the body. Axis system is that guy. I was missing this. I was missing a line there. I could have drawn a line there too. Would have done the same thing. And notice what it did. It kind of put this thing about the axis where it belongs to. Now, I think this problem I gave you the angular speed in, I don't know, in radians per second, but I think that it corresponds to 60 RPM. I think this number, oh no, 1,000. This number that I gave you, did I give you angular speed here? I didn't give it to you. 1,000 RPM. Okay, which turns into 113 degrees per second, radian per second. That's in the book. 1,000 RPM. I'll do it because the unit is already RPM. I don't want to change it. I'll put that 1,000. Okay. One last thing. In the last box, it says what is the angular acceleration. If it's going at a constant speed, angular acceleration is 0. Whereas this was a disk that starts from stationary condition and it builds up speed. To reach that, of course, there is an angular acceleration. So what you do is you calculate the stresses at the time where the acceleration is such and such. But for me, I'm assuming it has reached the steady state and turning at constant speed. 0 angular acceleration, which means constant speed. Just leave it. If you know what the acceleration is at that instant, plug it in and then get your stresses as you're supposed to. But this is constant speed. Okay, good. Save this and run it. Always pray because most of the time you need it until you develop some feeling for these things. Yeah. See? Without praying, it doesn't work. Your worst enemy. Well, do I know what happened? Let me cancel that. Okay. This is an indication that the structure is not properly restrained. Can you guess what's happening? Because of the things that I did, surface slider, essentially, turning at a constant speed. What is missing that ran into the situation? It can go up and down, right? As a matter of fact, if you don't see that, well, Katia will give you a hand and say, okay, show me what happened. There we are. Because the ends are on rollers. If I had used a third plane of symmetry with a roller on it, surface slider on it, this would not have happened. But I still have to fix it. I want to do it like that. So take away that rigid body motion. Okay, so deactivate this plot. When this guy is looking at you, there is nothing you can do. If I hear that on Friday, I'll try to rub it in. MECH is looking at you. Stress is looking at you. Deformation, displacement. There is nothing you can do as far as restraint. Deactivate this. So we take 1 point and say, hey, you can go up or down. So that is user-defined restraint right there, user-defined. 1 point. Now just be careful because remember I used the user coordinate system. Still user is showing. You may get lucky, but sometimes if you're not careful, up and down of the global coordinate system is that different from up and down of the local coordinate system. Here, definitely different. The local one has Y. The global one is Z. So if you want, you can use Y of the user because notice it's there. Or you can say global direction Z. Don't go up and down in the Z direction of the global coordinate system. And if you make a mistake, it will show on these plots, will show like this. See that red arrow in the corner? It shows. If you had selected the bad coordinate system, bad direction, you show in the direction that you immediately realize there's a problem there. Then we say, okay. And now we're going to run. And we are not going to get that message. We did not get that message. Can we look at the deformation? Can we animate? Why is this not moving? Why is this not moving? Because when it bombed out, it wanted to go to infinity. Katia says, hey, if you want to see something on the screen, I'm not going to use infinity. I'll make it 1,000,000 times smaller so that at least you can see something on the screen. And it keeps that until you reset the scale. And that is done in here. It's called magnification factor. And say default. There we are. And now animate. Okay? Now, it is not quite clear here. We got to look at it more carefully. It looks what it's supposed to. This disk is rotating. It scientifically goes out. It looks like that, but there's something that's bothering me right now. I'm not sure. Let's look at the contours of displacement, for example. They better be rings. They all go the same way. They better be rings. This is kind of tilting. I don't like that. We'll find out what's going on. Okay, so maybe not. I don't like that thing on the top. We're going to find out what the issue is. I have a problem with that one on the top. It's not much, but still I don't like it. The fact that these are supposed to go down, straight down, and they don't. Okay? So we must have something maybe wrong with our geometry. Restraints are straightforward. I mean, there's nothing seems to be doing. It's that geometry that I'm having a problem. Let's go to the geometry. The stresses are, again, they have to be circular pattern and they should come straight down. Okay, so let's look at it. I'm sure it will happen. That's better. If I want to see it not as smooth, let me uncheck that. Okay, view from the top. This stress looks better. I'm not sure why the other guy looked like that. Oh, what is this? No. Deactivate this. Let me look at this thing from the top. View from the top. Actually, it may not be that bad, but I didn't expect to have this different color here. But let's go and check our two things, the mesh refinement that we did. One face, let me deactivate that. Deactivate this plot. Okay, mesh refinement was there. The face was here. This is good. Where is that? Where is this? Oh, that guy is here because I selected it. It doesn't show up. It's right there. Let me make this thing a little bit smaller and run it again because I don't see why it looks like that. I don't see why this is all not the same color. It should be. Patterns look reasonable, but let me make this thing 0.05. And yeah, let's run it again. If still like that, I'll let you worry about it. You work it out because I don't see any particular reason that should be like this. This was translation, right? Why is that the case? I don't like it. These are supposed to go straight down. And let's do the following. Let's do the following. Let me go and delete that restraint that I put in there with a coordinate system that I created. This one I'm going to delete and put a surface slider there. Let's make a quick run. See, the stresses were nice and circular with things going straight down. That's why I don't understand. This is one meses. Deactivate. Displacement. I don't know. You can notice that, first of all, the fact that I changed the slider, replaced the slider with the other one, didn't make any difference. Okay, it looks they're both pretty much wrong there. It should not be like that, and you can worry about it. Okay, it should go straight down. Should not be light blue on the top. Okay. Now let's move on. Let's move on. Now I want to make a cut in the middle. Now I want to make a cut in the middle. So first of all, let me go to my part. Part right there. That looks good to me. You know, I was debating the geometry, maybe something. Let me take a look at the view from the top one more time before I give up. This goes straight through that. Yeah. I don't know why we're getting that effect there. Okay, so yeah. So I want to cut. I want to cut this thing in the middle. But unfortunately, when I modeled it, I didn't think about it. I would have symmetrically padded it so that there was a plane in the middle. No problem. Go create your own plane. So here's a plane. Offset from this plane, height of 0.5. Because this happened in the lab the other day. It said that, you know, I didn't make it like that. Okay, now go split it. Split it with this. Keep the top or the bottom. It really doesn't matter. There it is. And now we're going to go back to the end. Oh, save it. File, save management. This is the part. Save as. 3 planes, right? 3 planes. Okay. Cancel that. Okay. Let me also this. Save as. 3 planes. Save propagate directory and okay. Everything is safe. So the old one and the new ones are all there. Okay. So let's go ahead and run it. The only problem is in the analysis, I need to put another surface slider at the bottom of this. Okay. Because I don't have to fix it from going up and down anymore. So first of all, we can delete this. Where am I? I have to go back to the analysis. Good. We can delete this. But we put the surface slider at the bottom or the top place. I'll put it at the bottom place. And that's it. Nothing else. Save and run. That's fine. Okay. Let's look at the plots. First of all, deformation. Nothing exciting. That's fine. I can swear this guy is going sideways. I'm not sure why. Deactivate. Translation, that's where we had that. Well, that's gone. That's gone. Remember there was a little light blue on the top? It should not have been there in the first place. I don't know what I did. And one meter stress. Okay. There. Everything looks good. Biggest stress in the middle. Yeah. How was the displacement? Oh, displacement is the biggest on the outside. You know that already. And it was red on the outside. There. Okay. We solved the problem two ways. As in the book, did not use half plane of symmetry. That's why I had to say select one point and say it can't go up and down. Then I did it like that, halfway through, okay? And I don't need that restraint. That restraint would not have mattered anyway because you kept the bottom. It's going to complain to you that it's not there. You put it at a point that's gone already. It's okay, you would have run, but any questions? Okay. Doing it, without the plane of symmetry is the, I don't want to say hardest one. It is just that what point do you pick? Let's do it. So let's go to the part. You see. Let's go to the part. Save file save management. This is going to be save as. No planes of symmetry. You learn something. No planes of symmetry. Analysis. Which one is it? Is it 3 planes? Yeah. Oops. 3 planes. Save as. No planes. See, the other guys are there. No planes. I think it's better to say save, say propagate directory and then save. Okay. All right, good. Oh, ooh. Okay, I don't want to spend time on this, but let me move on and make the whole model. First of all, where is this cut? Split, gone, delete. Okay. Then I'm going to make this thing a circular pattern so 8 times so that I get the entire disk. Let me change the rendering here. Where is this? Where's my rendering? Oh, right there. Okay, go to the circular pattern. See if we can find a circular pattern here. Must be somewhere there. Oh, right there. This is a rectangular one. I want a circular pattern. 8 instances. 8 instances. Complete crown. Oh, let's check it out. Yeah, let's make it complete crown. And for neutral, for reference element, I select this. Whoa! No, it was 30 degrees, 12 times. I had to make it 12 times. It was not 45. 12 times. So double click on this. 12 times. Okay. Good. Sure. This is the full disk. And you know what? I will actually do another analysis for this. Okay. Instead of using the old one, the 3 no planes, I'll use another one. How about that? Analysis and simulation, generative structure analysis, mesh it, and let me kill this. Okay, so that everything is gone. Generative structure analysis, meshed. Sometimes it's better if you bite the bullet. Okay, you could have fixed it, but that's okay. Okay, so it is smaller, and it's just that the other guy is sitting on top of it. We can't see it. As a matter of fact, it's somewhere down here probably. Well, we'll find out. Let's forget the mesh. Okay, wait. If this thing pops up, you're in trouble because this doesn't tell you what the issue is. It says runtime. Usually, when we get runtime error, the system crashes. We'll see. That's why I should have saved it. I think I saved the part at least. So, you see? Save. All right, so let's, Katia completely bombed out. We can finish it. Don't worry. It's going to be quick. Why I got it? I don't know. In the lab, it happened once to some of the students, and he had not saved. You don't want that to happen on the test. That's what he saved. Recovered from previous session? No. These things usually don't work. Okay, so it was, I called it no planes, right? No planes. Oh, no planes. I didn't say, apparently I didn't save that last one. That's okay, we can do a circular pattern. See, that last one, it looks like I didn't save. So that's 12, complete crown. There we are. And that plane, that split, I should have deleted. Delete. Okay, good. This is where it ran into a problem. When I went to analysis and simulation, generative structure analysis is meshed it, but then I wanted to make the mesh smaller there. No problem, I can do that. So where is local mesh? On that face, did it pick both of them? This one and that one. And look, the reason we couldn't see it, just look. It's right there. One on this side, one on the other side. That's why I couldn't see it. But that's not the reason it crashed. So let's go ahead and say, okay. You want to look at the mesh? Something is wrong with this. Something is wrong with something is. It should work. There's no problem. But I get these runtime errors. So let me say a couple of words here. 2 minutes. No problem. We're not going to mesh it. We're not going to do a local mesh. I don't know why we're getting that message. And it looks like you get it when you do a local mesh for that particular problem. I still have 2 minutes. I'll finish it. Or at least I can tell you why we're going to have a problem. Okay. Okay. Close this. Get the troublemaker. No planes. Let me get rid of my split. And do a circular pattern. 12 of them. Complete crown. And neutral plane reference element is this. All right. We go to analysis and simulation, generative structure analysis. I'm not going to do local mesh. It has nothing to do with that, but I don't know. It could be that size, by the way, was small. Okay. Now, if this thing crashes, then there's something else wrong. Okay, that's fine. The local mesh I couldn't do. I have to admit. Now, deactivate this. Deactivate it. Oh, this is the mesh, right? This is the mesh. All right. So, the problem is this. This is turning in space. Load, no problem. I can specify the load. The load was that centrifugal force. The body is that entire thing. The rotation axis was, remember, I created this guy in the middle axis. Anything that's bothering you, just hide it. This axis, there we are, 1000 RPM. Okay. The problem is, what am I going to fix? There is no point there. It's not the box that has a corner as a vertex. There is no corner. Okay. It is possible to do it. I'm not going to do it for you, but I'll show you. I told you there's something that does it quick and dirty way, but if it's abused, it's going to crash. I mean, it's not going to work. It's not going to crash. It gives you garbage. So first of all, let me run it and convince you that actually it falls apart. So because I didn't restrain anything, it's just like a UFO flowing, spinning about its axis, moving in space. Okay, obviously you can see that. And you can look at the deformation here. That's what it wants. Okay, now, and the reason I'm showing it to you this year, let me first reset the scale here. Deactivate this. There's a reason. But if you use it and it comes out wrong because you're not using it correctly, you lose the marks for that particular part. There is something called, right here under restraint, see that? There is something that looks like an anchor. It says isostatic restraint. If you click on it, it puts basically that restraint here. You don't even see, you don't necessarily have to see it. It's right there. Here, look. It's right in the middle. It looks like an anchor there. And it's in the tree, by the way. Now let me run. Done. This anchor or isostatic restraint is nothing but that 1, 2, 3 rule that I did for you last week. It automatically goes and applies the 1, 2, 3 rule to some nodes that you don't see it. You can't see it if you want. You can find it. But it is exactly the same thing, but it does it for you automatically. So what I'm saying is that if you use this and get bad result because you just can't recklessly go ahead and use this, every time the problem doesn't work, do this. It'll run, but it's not the problem, it may not be the problem that you want to solve. So I don't want you to lose much on this. And the reason I did it is because already I put it on YouTube from last year or maybe the year before. So people, if they look, they come across it, but it is nothing but that 1, 2, 3 rule. It is exactly the same thing. As a matter of fact, let me deactivate this plot. Deactivate the plot. Let me get the mesh for you. Or, the mesh for you. And change the rendering to wireframe. I keep losing my rendering here. If you look close enough, you can find some points were fixed. You may have to look at the displacement. I'm not sure. Not in the mesh. Okay, perhaps not in the mesh. Deactivate this. Anyway, I don't know how to get it. But anyway, if you look close enough, you see that there is one node doesn't move in 3 directions. Another node doesn't move in two directions. A third node in one direction. It's exactly that 1, 2, 3 rule. This is it. So doing it the full thing this way is even more problematic. Planar symmetry helps you. Uh, I think I do this problem a different way, the full disk a different way in the book, but if you don't care, don't worry about it. All right, folks, so see you on Thursday.